Hello everyone, today we're going to develop an exercise taken from Eunice Sengel book on parallel pipes. The problem states that a cast iron pipe in a water distribution system is wrapped around a certain section. Both parallel pipes have a diameter of 30 centimeters, and the flow is completely turbulent. This information here about the flow being completely turbulent is important. Don't forget, one of the branches, in this case, the pipe is 1,500 meters long, while another branch, pipe B, is 2,500 meters long, and we can see that here in the figure. We have the branch, or pipe A and pipe B, both with 1,500 meters and 2,500 meters respectively. Also, both have 30 centimeters in diameter. The problem continues if the flow or flow rate through pipe A is 0.4 cubic meters per second. We also have that information here. Determine the flow rate through pipe B, neglect minor losses, in this case losses due to accessories, and assume that the water temperature will be 15 degrees. Show that the flow is totally rough and therefore the friction factor is independent of the number of. Okay, in this problem we need to pose a theoretical question for parallel pipes. If we have parallel pipes that divide from a trunk and then join in another trunk, we can write the following, which is the friction losses of both pipes are equal. In this case, I'm going to call pipe A1. I'm going to call pipe B2, and we know that these friction losses are given by the friction factor multiplied by the length times the velocity squared over 2 times the gravity times the diameter. In this case, it would be pipe A, and pipe, and that has to be equal to the friction losses in pipe B, which would be the same. But in this case, for pipe B, ready squared and all this, over 2 times the gravity, diameter of 2, very well. Here, it is important to know what data we have and what data we do not have. For example, we have the length in both cases. We have the diameter in both cases. We have gravity 9.81, and what we do not have is the friction factor in either case. However, we have the flow rate in the pipe. As I have the flow rate, and I have the diameter, and you know that flow rate is equal to velocity times area. If you have the flow rate and you have the diameter, it means that you can calculate the area. You automatically have the velocity, then velocity 1 is also data. What we don't have is the bending factor and the velocity in 2. But what they're asking me is to calculate the flow rate of pipe B, which would be the flow rate of pipe 2. If you calculate the velocity in this equation here, since you have the diameter, which is the area, you will automatically be able to calculate flow rate 2. In order to calculate this velocity 2, I necessarily have to calculate the friction factor in 1 and the friction factor in 2. How do I calculate the friction factor in both pipe A and pipe B? For this, we have the snake equation, or also the famous Moody diagram that appears below. In this case, for a better explanation, we're going to base ourselves on the new diagram. We have F, which is the friction factor. How do you use the Moody diagram, in case you've forgotten? Let's do a small example. The first thing you have to do is calculate the relative roughness. And what is relative roughness? It is the roughness of the material, which in this case is a pipe, here indicated as cast iron, over the diameter of the pipe. Okay, let's do the math quickly. In this case, it tells me the pipe is cast iron. In this table that appears here, which I also took from the book by Eunice Sengel, we are going to look for cast iron that appears here. Do not confuse feet with millimeters. In this case, we have 0.26 millimeters. So it comes to be 0.26 millimeters. But we have to work in meters so as not to get confused. This would then be by 10 lay minus 3 meters. And the diameter in both pipes comes to be 0. 3 meters, no. Since they are 30 centimeters, then the relative roughness to what is it going to be equal? It is going to be equal to 0.26 10 law minus 3 over 0.3. This is equal to approximately 0.0008. 6. Okay, without units, since here, meter by meter, it is eliminated very well. That comes to be our relative roughness. Let's give an example of how the Moody diagram is used. Let's say that in this case, the relative roughness has come out to be 0.02 very well, and that the number of Raynors has come out to be 10 to the 5th. It is over here what you have to do. In this case, we first follow the trajectory of this relative strictness. In this case, 0.02 is a random example that I'm using. We follow the trajectory, and we're going to intercept it with the projected vertical of the number of kingdoms. For example, if we're working in this case with 10, the 5th that would be here, we're going to intercept that here, more or less. Okay, why at this point? Because this point represents 0.002. Once you intercept the number of Raynors that you have calculated, which in this case I got 10, the 5th, I'm assuming, with the relative roughness of 0.02, which I'm also assuming that I got that value, once you intercept it, from here you are going to draw a horizontal. And that horizontal will indicate what the value of the friction factor is. For this hypothetical case, it is more or less above the value of 0.025. However, now that you know how the Moody diagram is used, I want you to observe the following. It is telling us that the flow is completely turbulent, and I had told you that this word is very important. Look up here in the diagram. In this area, it says laminar flow up to where the arrow indicates, and it says flow in transition, turbulent flow, and then it says flow turbulent, completely rough. No, so this part of totally turbulent and rough flow is the area that we are going to use. For what reason? Because here he is also telling me to prove that the flow is completely rough, and therefore the friction factor is independent of the number of rains. This red dotted line that you are seeing separates the completely turbulent rough flow from this area here. If you notice, all this area that is to the right side of the dotted line are practically horizontal lines. Practically horizontal lines. What does that mean, for example? If for me, the relative roughness had come out 0.05, what does that mean? That if the Raynors is 2 asterisk 10 the 6th, 10 the 7th, or 10 the 8th, it will not change what? The friction factor. Why? Because if you draw from here, for example, 10 the 6th to this value, or you draw 10 the 7th at that value of the relative roughness that more or less would be around here, and you also draw 10 the octave at that value, realize that this point of intersection with this one here, if you draw the horizontal line, you practically get the same value for the friction factor. No, it's practically the same. It's not changing at all. What does that mean? That means that when the flow is completely rough, the friction factor is independent of the number of Reynolds, because no matter how much the number of Reynolds increases, the friction factor is not going to change. Okay, this friction factor is not going to change. That is the demonstration that we can do using the mud diagram. No, then simply by calculating the relative roughness, I no longer care in this case about the number of Reynolds, because I am in the right area of this dotted line that represents that the flow is completely rough and it is a completely turbulent flow, and that is the condition that we are in the problem, because it tells us that therefore we are going to calculate now with the data that we have obtained a moment ago. The relative roughness in this case is 0.00086 practically, 0.0009. We look here in the table, and we are more or less at this point here. We are going to draw here with another color so that it can be differentiated. We are more or less at this point here. And if you notice, no. From here, we draw a parallel line. Practically, it is a horizontal line until I connect with the limit, which is this dotted line. I'm not interested in the Reynolds, because the number of Reynolds is independent, and from here you're simply going to draw what you keep projecting it. To draw what a line, until you calculate the friction factor, which, more or less, which is to say, we can say that 0.0191, we put there approximately, nope, then for pipe 1, the diameter is 0.3. For pipe 2, the diameter is also 0.3. As both pipes are made of cast iron, the epsilon between the diameter, for both cases it will come out to 0.0086. As both cases have the same relative roughness, they will have different numbers of Reynolds, but I don't care for what reason. Because I am in the completely turbulent and noisy zone, that means that the friction factor of pipe 1 will be equal to the friction factor of pipe 2. For what reason? Because I am precisely in this area here, to the right of this dotted line. Having that information, I can simplify this equation that is here. The friction factor of 1 goes with that of 2, because they are equal. Twice the gravity goes with this here. The diameter goes with this diameter, because they are 0.3 in both cases. And what would I finally have left? We are going to go down here a little to continue with the exercise. I would finally have pipe 1, which comes to be 1,500 meters, multiplied by the speed 1/2. This has to be equal to length 2, which is 2,500 meters times speed 22. In this case, I am going to calculate speed. 1 flow is equal to speed 1 times area 1, and the flow, which in this case is 0.4, comes to be equal to speed 1, which I still do not know, multiplied by the area, which comes to be pi times the radius squared. In this case, the diameter is 0.30, then the radius will be 0.15. All that squared of here I operate, and I'm going to get speed 1. That speed is 5.66 meters per second. We replace this speed where? We replace it here, and replacing that, we finally get speed 2. That speed 2 is equal to 4.38 meters per second. Very well. Now I'm going to calculate the flow rate in pipe 2, pipe B, which would be equal to speed 2 multiplied by the area, which is pi by the radius squared. Since the diameter is 0.30, the radius will be 0.15. Finally, from here I get that flow 2 is equal to 0.3098 cubic meters per second, which we can approximate, if you wish, to 0.31 cubic meters per second, and that would be the answer to the problem. Well, friends, I hope the explanation of the Moody diagram has been understood, and you know that if you have any questions or queries, you can do so in the comments. Greetings all.